Hello everyone, my name is Vanaret and I'm a PhD student at ICFP in Toulouse, France. I'm going to be presenting our implementation of an interval computation library for OCaml. In the first part, I'm going to introduce the motivation of such an implementation, then give a few details about the library, and then end up with a comparison of performance. At the laboratory, our fields of interest include global optimization. So given a particular problem where one aims at minimizing an objective function with possibly constraints, the aim is to find global solutions and compute guaranteed bounds on these solutions. To this end, we are currently developing a hybrid optimization method that combines a stochastic search with evolutionary algorithms and a deterministic search with interval branch and bound algorithm. And this latter requires the computation of both lower and upper bound of the objective function over a particular subspace. Interval arithmetic was introduced by Moore to bound rounding errors. Is there a pointer? Okay, no problem. I introduce here a problem. F is a polynomial function of two variables. If we want to compute the this evaluation, this is the exact value. If we compute it with the OCaml compiler, we obtain this value, which is far from the exact value. So hence the necessity to introduce interval arithmetic to bound rounding errors. Interval arithmetic extends to intervals binary operators, as well as elementary mathematical functions, for which an interval extension is to be computed to yield a rigorous enclosure of the image. Computations are carried out with outward rounding. Here's an example of the interval addition. The lower bound of the image has to be a lower bound of A plus C, and the upper bound of the image, B plus I D, has to be an upper bound of B plus D, so as to yield a rigorous enclosure and to guarantee conservativity in the computation. And if we apply this approach to the problem P I introduced before, we obtain for the evaluation, this one, we obtain the interval that obviously contains the exact solution.
And OCaml solution.
Sorry? Here are a few examples of interval arithmetic. The computation of the square function is rather straightforward. So minus 32 square is 0.9. For monotonic functions, it's pretty much straightforward. And for trigonometric functions, one has to study monotonicity. So sine of 1, 2, pi over 2 belongs to the interval, so the upper bound of the image is 1. And well, the lower bound image bound is computed by taking the minimum of the evaluation of the bounds. With these particular properties of conservativity, we can devise optimization algorithms based on subdividing the search space and evaluating the objective function. Here we have the search space into dimensions. We iteratively split the dimensions, evaluate the function on each subspace, and it allows us to discard immediately some of the subspaces. And when we obtain a pretty good solution here, close to the global minimum. It allows us to discard, well, the entire search list. There are actually a lot of existing interval libraries. Most of them are written in C++. Profile bias interval in Boost C++, jail, MPFI. The Sun interval library was written in Fortran 95. So why implementing a new library? We obviously have the preference for the functional paradigm of OCaml, and well, this particular algorithm has an exponential complexity. So there's potentially a lot of calls to the objective function. So this library has to be efficient. And to give you a few details now, when starting to implement the library, we quickly realized that mathematical functions in both C and OCaml languages do not return the same results on 32-bit and 64-bit architectures. This obviously may lead to wrong results in low rounding mode and high rounding mode. So we had to rewrite these functions in assembly language. Here are the different modules of the library. The first one, CHCW, is the implementation of all the elementary functions in the three different rounding modes, nearest, low, high. And these functions are written in C and assembly language. The floating point unit module is the binding to the previous module. The interval module is the proper module for interval arithmetic, and the last two modules redefine the OCaml floating functions. Here's the interface, well, part of the interface of the floating point unit module. The float function is exact on 32-bit machines, but not on 64-bit machines. So we had to redefine it for the three different rounding modes. So same thing for all the function, addition, subtraction, etc. In this module, we redefine the operators and the mathematical functions to ensure that they return the same results on all architectures. This is the interface of the interval module. So this is the basic interval type, the lower bound and upper bound. We define constants such as pi underscore I, which is an interval that contains the exact value of pi. We have conversion functions, addition functions between two intervals, between an interval and a float. And we have elementary functions, square root, and the power functions, etc. While implementing this library, we try to stick to a few ground rules. We do not compute empty intervals, because it would be a hard task to check if the interval is empty all the time. So we just raise an exception instead. We extend the set of reals to infinite bounds. And, well, the bounds are not supposed to be not a number. The lower bound is not supposed to be infinity, and the upper bound is not supposed to be minus infinity. And these three particular values are not handled as operands of the computation. Here's an example of the inverse function. If we compute the inverse of the degenerate interval 0, the computation fails. However, if the interval contains 0, then at least one of the bounds of the image is infinity. So it depends whether 0 is a bound of the interval or not. is the computation for a particular inverse function. If both bounds equal 0, then failure. If only a equals 0, then the upper bound of the image is infinity, and the lower bound is inverse b, rounded downward. If a and b have the same sign, then it's pretty much straightforward. And if b equals 0, the lower bound of the image is minus infinity. The upper bound is the inverse of a, rounded upward. And if 0 belongs to the interval, then we have the great image interval, minus infinity, infinity. I'm going to give a few points of comparison with binding to MPFI over a million operations. So the blue curve is the MPFI binding, and the orange one is our native implementation. The left part regards the binary operators. The right part is the a few mathematical functions. As we can see on the left part, our library is twice as fast as the MPFI binding for basic binary operators. You can see on the right side, it's 20 times as fast as the MPFI binding. So, despite the fact that MPFI modifies the interval in place, it means that the result is created once and for all at the beginning of the computation and modified in place. I have presented a native implementation of an interval library, which required to redefine all the elementary functions in low-level languages. It's a reliable library. It is fast, despite the fact that we have to compute, allocate a lot of intermediary results. And we successfully use this library in our hybrid algorithm I mentioned before. We were able to improve the optimal results of the Michaelis function. It's a benchmark function. And we solved also optimization problems concerning aeronautical applications. If you have questions about details, implementation details, you can contact these two people. Otherwise, I'd be glad to answer questions.